In this lecture, we'll talk about the independent samples hypothesis test for two means. In this case, we'll do one example where the two population standard deviations, sigma 1 and sigma 2, are known. And then in the second example, we'll do one where the population standard deviations, sigma 1 and sigma 2, are unknown. If we want to compare two populations, we're often interested in which has the higher or lower mean. This hypothesis test will show us how that comparison is made statistically. Here are some examples of situations where you might need to test one mean against another. For instance, does the average height of American males differ from that of Dutch males? We probably are unable to get data from every single American male and every single Dutch male. So instead we have to take samples and hope that the samples tell us what the true population actually is in terms of average height. Another example, do people taking a drug have a lower average time of recovery than people taking a placebo? This would be in a medical trial. And a third example, are average TV ratings higher at 6 p.m. or 7 p.m.? We're not likely to be able to sample from every single TV area always at 6 p.m. and 7 p.m. for, say, an entire year. We'd probably have to gather a representative sample from just a few weeks, from just a few areas, and use that as a representative sample of the entire population of TV ratings in various areas of the country. Here's an example problem. A survey of 1,000 students nationwide showed a mean ACT score of 21.4. A survey of 500 Ohio scores showed a mean of 20.8. If the population standard deviation in each case is known to be 3.0, can we conclude that Ohio is below the national average at the 5% level of significance? Again, we're asking if Ohio performs on average lower than the rest of the country. So we're going to compare Ohio's mean to the national mean. Here I have two different means. I have the mean with a subscript O for Ohio and the mean with a subscript N for national. My researcher's hypothesis is that Ohio has a lower mean than the national mean. Thus, the null hypothesis is the opposite, that Ohio is just as good, if not better, than the national mean. Notice with a quick algebra step, we can subtract mu n from both sides, and then we end up with the difference between Ohio and the national average is greater than or equal to 0 versus the difference of the Ohio and national average is less than 0. These are equivalent hypotheses, but it may help to write them in this order when we create the test statistic. In step 2, as usual, we gather data from the samples. You may want to go back and read the question again to make sure you know where these numbers are coming from. We saw a sample mean from the entire United States sample of 21.4 with a known standard deviation of 3.0 and a sample size of 1,000. The Ohio sample turned out an average of 20.8 on the ACT with the same known standard deviation and a smaller sample size of 500. Here we wish to test at the 5% level of significance. In step 3, we typically calculate a critical value and compare it to a test statistic. In this case, I've provided the formula for the test statistic. The general formula is taking the difference between the two sample means in the numerator and dividing by this denominator, the square root of the first population variance divided by the first sample size plus the second population variance divided by the second sample size. So if we steal those numbers from part 2, we get this equation. Notice the direction that I subtracted in this case was the national average minus Ohio's average. If we had subtracted in the opposite order, we would have just gotten a test statistic that was negative instead. Our critical value in this case comes from the 5% one-tailed column of your t-tables all the way down at the Z row, the bottom row of the table. So this is equivalent to going to the t-table, to the infinity row, or the final row of the t-table, and the 5% column where we put the one-tailed 5% area off to the side. That value should be 1.645. Recall that in our decision step, If the test statistic is more extreme than the critical value, then we must reject the null hypothesis. In this case, 3.65 is indeed farther from 0 than 1.645, and so we reject the null hypothesis. Note that had we subtracted in the opposite direction by doing Ohio minus the national average, we simply would have gotten negative 3.65, which still would have been farther from 0 than 1.645. In this case, either way, we'll be rejecting the null hypothesis. The key here is to realize that the national sample mean was higher than the Ohio mean, and thus there was some evidence to reject the null hypothesis. In our case, there was enough evidence to reject the null hypothesis based on the 5% level of significance. Thus, our interpretation is there is sufficient evidence at the 5% level of significance to claim that Ohio students' average ACT scores are lower than those of the entire country. To our second example, in this case, we wish to test for evidence that Leo Tolstoy uses bigger words on average than J.K. Rowling. We took a sample of 12 chapters from each of Tolstoy's War and Peace and Rowling's The Sorcerer's Stone. Tolstoy's sample recorded an average of 4.46 letters per word, with a sample standard deviation of 0.17. Rowling's sample recorded an average of 4.28 letters per word, with a sample standard deviation of 0.15. Is there sufficient evidence at the 5% level of significance to claim that Tolstoy uses bigger words than Rowling? Note that just 12 chapters of one book from each author is not a large enough sample to constitute a full population. But hopefully there's enough evidence from this sample to suggest that one author, Tolstoy in this case, uses bigger words. Also note here that we're using sample standard deviations, not actual standard deviations, and thus we're going to need to change our testing procedures slightly. The hypotheses in this case are that the average from Tolstoy is greater than the average from Rowling, and in this case we're talking average letters per word. Thus, the null hypothesis is that Tolstoy is no greater than Rowling, that is, less than or equal to. Again, you can rewrite the hypotheses using subtraction if you just subtract the mean of Rowling from each side of the inequality. And now, this might be the best way to subtract them in the test statistic later. In step 2, as is typical, we gather data from the samples. Reading above, you'll see that Tolstoy's average letters per word was 4.46, with a standard deviation of 0.17, and a sample of 12 chapters. Rowling's sample average was 4.28 letters per word, with a sample standard deviation of 0.15, and a sample size of 12 chapters again. In this case, we need to know the degrees of freedom for this test. Typically, we just have one sample size, and we do the sample size minus 1. But in this case, we have two sample sizes, and it turns out there's actually a really complicated formula for the degrees of freedom. You can calculate the degrees of freedom using the information from step 2 and this nasty formula. I don't suggest doing this, and we'll find later that the calculator can be very handy for this step. However, if you do go through the process, you should calculate the degrees of freedom as being 21.66, and we will always round this down to the highest integer below this value, so that would be 21. Recall again that we must calculate a test statistic and critical value as part of our critical value method in step 3. In this case, the test statistic looks very similar to the first test statistic we talked about, except we're going to use sample standard deviations and sample variances instead of the population variances in this part of the calculation. So I take the difference between Tolstoy and Rowling's means, and I divide by the square root of the sample standard deviation squared, otherwise known as the sample variance, over the sample size, plus the sample variance of the second sample, divided by the second sample size. Check on your calculators to make sure that you get 2.75 as well. Now in this case, the critical value will still come from the 5% one-tailed column, but we have to go to 21 degrees of freedom this time because we're using a t-distribution, not a z-distribution. That critical value should be 1.721. In step 4, recall that if the test statistic is more extreme than the critical value or farther from 0, then we must reject the null hypothesis. 2.75 is indeed farther from 0 than is 1.721, and so we reject the null hypothesis. Here in step 5, we see that there is sufficient evidence at the 5% level of significance to claim that Tolstoy writes with bigger words than Rowling on average. Impressive considering the number of Dumbledores that show up in the Sorcerer's Stone. Now let's do the test on the calculator. Here I've gone back to example 1 and shown you the step 2 gathered data that we can punch into the calculator for this test. Because we know the population standard deviations, we're going to go to Stat, Tests, and we're going to go to a 2-samp z-test because we're using the z distribution here. That's due to the fact that we know the population standard deviations. Here I want to input from stats. My 2 sample standard deviations are 3 and 3, so that's good. The sample mean from the United States was 21.4, and the sample size was 1,000. The sample mean for Ohio was 20.8, and the sample size was 500. In this case, choosing the alternative hypothesis can be a little bit trickier because it depends on which order you entered the sample means. Here I entered the US sample mean first and the Ohio sample mean second. And I'm trying to argue that the Ohio sample mean is less than the United States sample mean. But because I've entered it in this order, I have to tell the calculator that I'm testing for the national mean to be higher than the Ohio mean. If you think about it, saying that Ohio is less than the United States is the same as saying the United States is greater than Ohio. The calculator is just picky about which order you enter. So I need to make sure here that I choose the greater than mu2 because I'm trying to say that the United States is greater than Ohio. Now we go to calculate, and you should recognize that test statistic of 3.65. In this case, we have a p-value in scientific notation. This tells us to move the decimal point 4 units to the left, thus creating a very small p-value of 0.00013. Again, a p-value that small would reject the null hypothesis, and we would come to the same conclusion that we did down here in step 4 when we did it before. In the second example, we didn't know the true population standard deviations. So on our calculator, we need to go do the 2-samp t-test instead of z-test. In this case, many of the inputs are the same, except we need to enter sample standard deviations. So here I'm going to enter Tolstoy's sample letters per word, on average. His sample standard deviation was 0.17, and his sample size was 12. The second mean was Rowling's mean, 4.28 letters per word, 0.15 sample standard deviation, and also a sample size of 12. Now in this case, I'm arguing that it was Tolstoy's mean that was higher than Rowling's mean. That's what my hypothesis says here. Because I entered it in the order Tolstoy first and then Rowling, I still want my greater than hypothesis. We will never pool the variances here, so keep pooled as no. And now calculate. Again, that test statistic should look familiar, 2.75. The p-value of 0.00588898 is well below 0.05 or 5%. In this case, we would reject the null hypothesis as we did before. Notice here the degrees of freedom would be calculated as 21.66, as I indicated right here.